One type of problems which we didn't discuss in class, but potentially very important, and you need them for your homework, is the problems which involve also switches in the circuits. And here's a problem which was actually in our in class, but we didn't have time to go through it, and I redrawn it over here. So here we have three batteries: battery number 1, battery number 2, and battery number 3. We have two loads with resistance R1 and R2. Additionally, we have a switch included over here. Okay, so when we deal with switches, we need to know how to deal with the associated potential differences. But first things first, I would like to first indicate all the currents over here in the circuit. So I will start by, per our rules, I will start with labeling all of them and giving them direction. So I will first start with the current through the battery number 1, and I will label it I1 over here. And I selected this direction, which to me is kind of natural over here. So I1 will flow in this direction over here. So, and here we'll have I1. So I1 starts from here, right, and it flows through the battery, then through the load over here. So now let's also introduce the current I2. So this is the current through the battery number 2. Okay, so it will flow in this direction over here. Okay, and finally we'll have the current I3, and it can potentially flow through the switch if the switch is closed, and will flow this way, and we also will flow through the battery number 3. All right, so now we named all these currents, so I will also name the nodes. So this is node 1, and this will be node 2. Here I will only need the node 1 actually to specify all I need about the conservation of the current. So over here I already wrote the rule, so it's all incoming currents, and it equals the sum of the outgoing currents, and the outgoing currents is I2 and I3. All right, so as a matter of fact, so let me also specify what is given. So all EMFs of all the batteries are given, and the resistances are given. What what we need to find, that kind of depends on the problem. So in principle, we can find all the currents in this problem, and we can find the potential difference across the switch if the switch is open. Okay, so we specified that. So now I would like to also specify the potential differences across each device. So for the batteries, it's always from short to long terminal, from short to long, from short to long. Okay, for the resistances, is for the loads, it is always against the current, and that's it. So there are two loads. So now I want to specify the potential difference across the switch. Here you can always just come up with some guess. So I came up with this guess for the potential difference across the switch. But if you come up with a different guess, then you'll just get the negative answer. But that's okay. It will be also the correct one. So I just came up with this potential difference, with this direction of the potential difference. That I'm going here from low to high in this way. So I will specify the loops. Okay, so the loops here I will consider two loops, and I will consider the small loops L1 with this direction, and L2 with this direction. I will write the corresponding equations for the potential differences across each loop. So here I got the equation L1 and L2. Please pause the video and cross-check me. So here, when I was going through L2, I took into account the direction of the potential difference when I go around this loop coincides for the switch coincides with the potential difference for the switch, and therefore I have a positive sign over here. Additionally, for each, whenever I was computing this loop, I already substituted what I know for each resistor, that the potential difference across a resistor So delta V is given by I times R, and I already substitute into the loop equation. Okay, so now we can consider two cases when the switch is open and when the switch is closed. We will start first from the case number one, when the switch is open. If the switch is open, okay, that means that there is no connection over here. Okay, there is no connection over here. It means that there is no current. The current cannot flow if there is no connection. If the wire doesn't form a closed loop, there might be no current. Okay, so there will be no current. So that mathematically means that I3, this current, is just zero. So in other words, there is no current through the battery number 3. So I3 is zero. What we need to find actually this potential difference, delta V switch. Okay, let's proceed. So from the equation number one, for the node, since I3 is zero, we'll be able to find that I1 equals I2. Okay, I1 equals I2. Let's substitute this fact to the equation L1. Okay, to equation L1. So here we had I1 and I2, but we know that they're equal to each other. Let's, instead of I2, substitute I1 and simplify equation L1. We will obtain the following equation, from which we immediately will be able to find I1. Okay, you can substitute the numbers at each point of these calculations. I'm not substituting the numbers until I get the final result, but again, you can substitute the numbers over here. Epsilon 1, epsilon 2, R1 and R2 are given. Okay, but we also established that I2 equals to I1, and therefore we will know I2, right? So I2 will be known, it's the same as I1. So now let's use this fact and substitute this to L2. Okay, substitute to L2. So L2 involves delta V switch, which we want to find the voltage across the switch, right? So the potential difference across the switch, and it involved also I2 over here. Okay, so but I2 we already found, right? I2 we already found. We'll substitute it into this equation to obtain this. Okay, we will have a little bit reshuffle the terms. We will get epsilon 3 minus epsilon 2 plus delta V switch. Okay, so this is all follows from L2 plus this combination which we found to be I2 times R2 equals 0. Okay, and we can simplify this in order to find delta V switch, to transfer the terms to the right hand side, and we'll obtain this result, to which we can substitute now the numbers. But again, so you can substitute the numbers at any point. Epsilon 2 is 12, epsilon 3 is 2 volts, epsilon 1 is 4 volts, epsilon 2 is 12 volts, and each resistor is 2 ohms. And from this, you'll be able to obtain that the potential difference across the switch is 2 volts. Is 2 volts. Okay, so we know this potential difference will be 2 volts. Perfect, fantastic. So and the current through the battery number 3 is 0 only because the switch is open. All right, so now let's consider also the case where the switch is closed. Okay, the switch is closed. Okay, so if the switch is closed, so there will be current now. Okay, but if the switch is closed, then the potential difference across the switch is 0. The switch is closed. That means that the wire has an equipotential surface, right? And since it's equipotential surface, then the delta V is 0. Okay, so if it's just a piece of the wire, so the switch is closed, then there will be no potential difference. That will help us to simplify the equation for L2, because this contribution here will disappear for the case number 2 when the switch is closed, right? It will just disappear. Okay, but what we want to find? Actually, we want to find here the current through this third battery. I mean, you can find the current through all the batteries, but I would like to just find the current through the third. Okay, so the current is not 0 now because the switch is closed. But what is 0 is delta V of the switch. So from L2, I'm just rewriting L2. So I get these differences of the EMFs. Okay, times plus I2 times R2, and there was this unknown delta V switch, but as we established in our discussion, this is 0, and therefore from this equation we can immediately solve for the unknown I2 and to get this current I2. Okay, now let's use this result and substitute it to L1. You remember that L1 also involved I2. Okay, if we do that, we will obtain the following equation over here, which I a little bit simplified. Over here, simplified, cancel some of the terms with different signs, and I obtain this equation for I1, which I can immediately find. I1 will be epsilon 1 plus epsilon 3 divided by R1. Okay, so now I found I2, I found I1. But remember that the node equation combined as I1, I2, and I3. So from this equation, I will be, so I1 and I2 I found. From this equation, I will be able to find I3. I3 is going to be I1 minus I2. I will just substitute these analytical expressions over here for I1, analytical expression over here for I2. You should substitute the numbers. I just prefer to deal here with the symbols, with the variables. But you should substitute the numbers. So when I compute this contribution over here by using the numbers given, I will get 5 amperes. For this, I will get 3 amperes. The difference will give me the final result of 2 amperes. This will be the current through the third battery over here. Okay, so in principle, after that, you will be able to find the current through the second battery and through the first battery. But we essentially just did this. So this would be the current through the first battery. This will be the current through the second battery. So this is pretty straightforward how to do. This essentially concludes this type of problem. So the only thing here I wanted to actually discuss in detail is how to treat the switch.